I'll be presenting our paper titled Asynchronous Majority Dynamics in Preferential Attachment Trees. The broad motivation for this work is how opinions form and spread in social networks. Individuals make decisions using a combination of their private opinions as well as social influence. And we're interested in how the structure of the network can give rise to different behaviors. When will there be collective learning or echo chambers? Our model is as follows. Each node is assigned a binary private belief, independently at random, with a bias towards some ground truth, say opinion 1. So xv will denote the private signal of node v. So the probability that v will have signal 1 is 1/2 plus delta for some constant delta. These private beliefs are not known publicly, but they're revealed through the following asynchronous process. At each round, one node is chosen uniformly at random to make an announcement, and it will do so by considering its neighbors that have already announced and taking the majority of their announcements. In the case of a tie, it will announce its own private signal. Here's a quick demo of our model. First, each node is assigned a private belief independently with a bias towards red. Then, one node is chosen uniformly at random to announce. And since none of its neighbors have announced yet, there is a 0-0 tie, which he will break in favor of his own signal blue. Okay? Similarly, no neighbors have announced here, so she will announce her private signal red. Now, this node here sees a single neighbor that has announced blue, so he will copy. And this node sees a 2-1 in favor of blue, and she will announce blue. Finally, this node is chosen again, and this time sees a majority of blue, and it will change to copy its blue neighbor. Okay. Next, let's consider a few examples of network structures and see what they will give rise to. In the case of a complete graph, everyone will copy the first node to announce. So in particular, there is a 1/2 minus delta chance that the first node has the wrong signal and the network stabilizes in an incorrect consensus in that case. So this graph is really dense and it doesn't allow for independence, and therefore the bias doesn't get to show. Now let's consider a different graph, a sparser graph, a star. Before the center is chosen to announce for the first time, all of the leaves are independent. So chances are a decent number of leaves will announce before the first time the center is chosen, and the majority of those leaves will be correct because of independence, so the center will copy that correct opinion, and then everyone copies the center. Therefore, a star stabilizes in a correct consensus with high probability. Finally, let's consider a path. If any two neighboring nodes have the same signal and are chosen to announce before there are two neighbors on the path, they will forever reinforce each other's announcements and form a roadblock. So a path may not even stabilize in a consensus in either opinion. However, it's still reasonable to ask whether it stabilizes in a correct majority, and turns out that is the case for a path. In fact, every graph stabilizes in polytime with high probability, and maybe we can hope for showing sparse networks stabilize in a correct majority. There is a lot of prior work studying information spreading in graphs under a variety of models, and the one in particular that studies our asynchronous majority dynamics is by Feldman et al. And they showed that in expanders with constant max degree, the process stabilizes in a correct consensus. Their proof has two disjoint parts. The first part uses sparsity and claims that up until near linear steps, most of the nodes have the correct announcement. And this is roughly because nodes that are far from each other are still independent at this point, and having constant max degree means that most nodes are far apart. But after near linear steps, the independence argument fails, and nodes may start to become dependent. And so they have to show that the correct majority won't be lost before stabilization. So their second part of their proof is to invoke expansiveness to argue that once there's a clear majority, it spreads to the whole graph. Our paper relaxes some of these assumptions. In particular, the constant max degree assumption is limiting because real-world social networks often have nodes with high influence, the so-called hubs. So here's our main result. We show that the process stabilizes in a correct majority with high probability in two classes of trees, preferential attachment trees and complete Emery trees. I'll define these in the next slide, but a quick overview of our proof. Our proof has two parts, similarly to the previous work. The first part is again that after near linear steps, a clear majority is reached. This is the same statement as prior work, except they showed that for all graphs with constant max degree, this holds, but we show it for all trees, regardless of degree. The second part is, again, to show that this correct majority won't be lost until stability. Prior work used expansiveness to get this, but since trees aren't expansive, we developed new techniques to show this for the two classes of trees, which I'll define soon, but I just want to point out that in proving part 2, we also give a tighter bound on how fast this process stabilizes in any graph, where dg here is the diameter of the graph. There are some definitions of the classes of trees we'll work with. Preferential attachment trees are generated according to the following process. We have end nodes that arrive sequentially, each attaching a single edge to a pre-existing node at random, proportional to the degree of that node. So specifically, we have V1 to Vn arriving one at a time. There's a special node V0 that only V1 connects to when V1 arrives and no one else connects to V0. And then when Vi plus 1 arrives, it attaches a single edge to a previous node, which it will choose proportional to, with probability, the degree of that node at that time with some normalization factor. And balanced Emery trees are trees that can be rooted at some node such that all non-leaf nodes have m children and all leaves have the same distance from the root. Now back to our proofs. The first part is to show that after a near linear number of steps, with high probability, there is a correct majority. We will first show that after t roughly n log n over log n steps, in expectation there are half plus delta n correct nodes, and then we use Chebyshev's to get a high probability statement. Now we want to bound the expected number of correct nodes after t steps. We can directly use this theorem from Boolean function analysis, which says that an odd monotone Boolean function of n bits, each sampled IID with bias p at least 1/2, will have expectation at least p. So fixing a node v and an order of announcements, the announcement of v is an odd and monotone function of all the private signals. It's odd because flipping all the signals causes v's announcements to flip, and it's monotone because changing a private signal from A to B can never make v's announcement go from B to A. And it immediately follows that the expected number of correct nodes at any time is half plus delta n, minus the nodes that may not have announced yet. But by t equals n log n over log n steps, all but a small number of nodes have announced, so we basically get a half plus delta n majority. So the details of this are in the paper. The next step is to show that after near linear steps, a correct majority exists with high probability. Roughly speaking, we want to use Chebyshev's inequality, so we have to bound the variance of the number of correct nodes. And we do this by showing that most pairs of nodes are most of the time independent. More formally, we say that two nodes u and v are epsilon disjoint at time t if there are two independent random variables xu and xv, such that the announcement of u is xu at time t with probability 1 minus epsilon, and similarly the announcement of v is xv with probability 1 minus epsilon. And if we add up all of these epsilons for all pairs of nodes and call them d, it turns out that Chebyshev's gives us a concentration bound as a function of d. And in particular, if d is little o of n squared, this term vanishes as desired. So our task is now reduced to bounding the sum of these epsilons to be little o of n squared. Here's an overview of how we accomplish this. We consider one pair of nodes u and v, and depending on the path between them, we analyze them in one of the following cases. If the path between u and v is long, information won't get to propagate by n log n over log n many steps between the two. And also, if the path between u and v is short, but it's a low degree path, in particular if the product of the degrees of the nodes on that path is small, a counting argument shows there can't be many of these paths, so they don't contribute that much to the sum. Finally, if the path between u and v is short and the product of the degrees on that path is large, then there must be a high degree node that only ever announces correctly, and that forms a roadblock that makes u and v independent. For the long path case, we show that the disjointness of u and v is exponentially small in the distance between them. Just because for some signal to reach both u and v, nodes from the middle of the path will have to announce in order along this long path, which is unlikely. For the short, low-degree path case, we show that the set of paths with product of degrees less than x is at most xn over 2. This is done inductively. We don't go into it here. Finally, for the short, high-degree path case, we use this proposition to argue that there is a roadblock on the path. Any node v always announces 1 up to n x spin the degree of v steps with probability at least about 1 minus constant over degree of v. Even if we force a constant number of nodes to always say the wrong thing. Intuitively, what's going on is if v has a high degree, all of its neighbors are independent until v announces for the first time. And if v announces really early before its neighbors, which happens with probability proportional to its degree, maybe it says the wrong thing. But this proposition says v announcing really early is the only bad thing that can happen. And otherwise, v will always be correct, even if its on-path neighbors are adversarially announcing the wrong thing all the time. So from here, we can show that a short high-degree path must have a high-degree node that in turn this proposition applies to and acts as a roadblock. Okay, so this wraps up the first part of the paper. We have shown that after slightly superlinear steps with high probability, there is a correct majority. And now in the next part, we have to show that this correct majority is maintained to the end. So we do that by showing that in certain trees, most of the nodes will have finalized after near linear steps. So we define an XY leaf to be a node that has at most X descendants and height at most Y for some rooting of this tree. For example, every real leaf is a 0,0 leaf. We define a node to be finalized if no matter what, it will never change its announcement again. And we say a node is nearly finalized with respect to U if the only reason it will ever change is to copy U. And it will copy U until it finalizes. So all leaves are nearly finalized with respect to their parent, for example. But so is this node here in this picture because its children are finalized in a tie. So this node can only change to copy its parent, and once its parent finalizes, this one does as well. So this theorem tells us how fast an XY leaf gets to a nearly finalized state. In particular, if V is an XY leaf, with probability X times X minus T over Y, V is nearly finalized after T steps with respect to its parent. So it uses this lemma. So first observe that each time a node changes its announcement, that's caused by a fresh announcement. We can track it back to a fresh announcement for the first time, making its way to this node for the first time. Now define TV to be the first time all the fresh announcements from all the descendants of V have reached V. Then we have a lemma saying that V is nearly finalized now. So this allows us to not wait for the whole tree's fresh announcements to hit V, because it's enough to wait for just the descendants. So we wrap up with the following corollary, which says nearly finalized nodes imply the existence of a lot of other finalized nodes. So even though they're not finalized themselves, they mean there are a lot of other finalized nodes, which is necessary to wrap up. So I'll leave it at that in the interest of time. So to wrap up, we apply these theorems to our two classes of trees. For preferential attachment trees, it turns out most nodes are in good subtrees in the following sense. So a subtree rooted at V is good if it has polylog many descendants at most, and at most log n height, but the parent of V has high degree, at least polylog. And the high level idea here is that most nodes are in a good subtree. So they become nearly finalized by the theorem we just showed. Also, the parents of these subtrees have high degree, so they are always correct by the short path high degree argument we just showed. So once the subtree is nearly finalized, it also becomes finalized quickly. For n-ary trees, when n is large, then every node is always correct by the short path high degree argument we gave earlier. So we only need to care about when m is small, in which case every node at depth h is a 2m to the h leaf. So in particular, for all nodes of height up to log n, applying the theorem we just showed, we know they become nearly finalized after n log n over log n many steps. And then we show that in n-ary trees, nearly finalized nodes have a lot of finalized children. And these finalized children have only finalized descendants. So we get that most of the nodes are finalized, which finishes the n-ary tree treatment. So in summary, we have shown that in a near linear number of steps, there's still a lot of independence within the opinions, and a correct majority exists with high probability in any tree. And then we show that in some trees, the process becomes mostly stable pretty quickly as well, allowing us to stabilize in a correct majority. And we showed this for preferential attachment trees and balanced n-ary trees. The main open question about this line of work is our conjecture that this process stabilizes in all trees. And even more general than that, maybe a result can be shown about graphs with bounded arboricity, where arboricity is the smallest number of trees needed to cover the edges of the graph. So trees have arboricity 1, etc. Thank you for listening.